screen that you don't know why it's there, ask, please, because you don't want to be wasting time. Otherwise, then what are you doing? So this is about you learning and gaining the knowledge that you need to do well to get into whatever program you want, so that you can, have a career and life and things like that. So you don't want to be remember that you're in control. Okay, you don't want to be having to depend on whatever marks you get and then try and see where you can fit in. You want to know that whatever marks you get, you're going to be able to do what you want. So you want to create a situation for yourself where you are free to do what you like without having to let that be to external factors. Okay, you have more control than you think. All it takes is a little bit of dedication and some work. All right. So I'm going to be writing here. Hope this moves. Okay, perfect. Cool. And draw. Use blue, and you guys you're allowed to use either blue or black pens. In uni, we're only allowed to use black. Let's go with more colors. Let's like this blue. Okay, so the top, again, we're pretending it's a paper. So write your name. I'm gonna write my name here. So towards the end of the year, or more actually towards assessments, this is what I do. So this was one of my techniques. I took out a blank page, pretended in front of me, pretended it was the exam paper, and then I'm answering it. And then I just did that. And then I watched my time. I saw how long I took. I saw where I found difficulties. I saw which was the parts were easy. I sort of found a format to answering the paper. And that's what I want to go through with you as well, because it was a technique that worked very well for me. And I want to show it to you as well, because I think you can use it. So more towards the end of the year, you'll be doing things like this. But I think it'll help a lot to apply it here as well, because it's the same things. So I'm using a November paper. I know I said March paper in the group, but I don't use March papers for revision at any stage in the year. And you guys know why. Okay, the March papers, the September papers, the June papers, they're not national questions. Those are only provincial-based questions. And a lot of your provincial examiners, like Gauteng or KZN, they can't create entirely new questions without the exam board authority. And the only way they can do that is if they are actively setting national papers at the end of the year, and very few are. So chances are the people that are setting your papers for March, for September, for June, don't have that national experience. And if you practice with those subpar exam questions and exam papers, you're not going to be in a very good position for finals, because that is the end goal. Finals is 75%. 3/4 of your results come from your final exam paper, that one paper. The 25% is every other assessment that you wrote throughout the year, not as much. So you want to make sure. So they try as far as possible to mimic a final exam scenario, but they often fail. Okay, it's not a very nice thing, but it happens. They don't do it very well. So you as a student have to take it upon yourself to make sure that you are doing the most efficient revision method possible, which is only working with final exam questions, because they often adapt these questions for your March papers, for your June papers, for your September papers, again, because they don't create new ones, they just recycle. And you'll find that happening very often. So a lot of these questions here, you will see in my revision pack, you'll see it in at least maybe one or two, you'll find it in your year, whatever happened. Oh, yeah, so these things are repeated in the March papers, you'll find stuff like this, okay? So we're gonna start, so your name, and then write November 2016, DBE or NSC, whatever you're gonna write, physics, paper 1, okay? And then we start. What do we write? If you do this, no, okay, that's wrong. We start with question 2. Okay, for physics, you don't ever start with question 1, you start with question 2, because question 1 is multiple choice, and that assesses your entire syllabus. So you don't want to be having to just get thrown into everything at the same time. It doesn't work very nicely when your brain has to, because your brain is a very systematic organ. It likes putting things, it's OCD, okay? Even if you're not, your brain, the way that it learns, it packages things. So if you're jumping into everything at the same time, it's going to jumble information around, and all the pathways are going to be activated, and it's not going to be a very, very nice. So it's better if you were to do it, what's this? Whoops, okay. If you were to start with your questions, your long questions first, and then come back to the multiple choice when you've covered everything in detail, so that you can remember and do better. Okay, so we start question 2. Question 2 will always be a Newton's laws question. In your final paper, sometimes even question 3 is Newton's laws. Okay, so this is a very nice question. forces. Let's answer it together. Give you a moment to read, and I want you to be writing as well. Whatever I have on the screen, you must have that and maybe more, okay? Oh, but anyway, I won't put too much here because this is just for, I'm pretending it's an exam paper and how I would answer it. So I'm not going to be doing too much notes, okay? So it's fine. So we're going to start not with 2.1. We don't do that. Remember, the first thing you do when you start your question is that you draw a schematic, and then you work with your schematic a little bit, and then you use that schematic as the basis for answering your questions. That's how we do it, okay? I know you want to jump right in, but don't. So you're allowed, before you say 2.1, 2.4, whatever the case is, to just do a rough diagram. I always do that. I find it helps a lot, and it does. So just my horizontal surface that's shown there. This is the margin of the page. Okay, so this is what you should have. Our 3 kilogram block there, and there's a rope. Okay, or as massless inextensible cord. What does massless inextensible cord refer to? Now we know that there's going to be tension. We know we're going to be working with tension somewhere along the lines because that's what tension is. Okay, and here is 1.5 kilograms. It's a second block. And what's happening here? That's interesting. Now, force is acting on it at an angle. These questions are quite interesting. They don't come out too often, but they're nice when they do. And this angle is 30 degrees, and this is a force F, okay? Equals F applied equals 25 Newton. So they changed things up a bit in recent years. So up and down, they just choose. The exam council at the time decides which symbols they want to accept as being allowed in the exam. So like W for weight, for instance, it's more appropriate, even though it's the same thing, to write FG, the force of gravity. They even allow the force of the weight force, rather. So that's allowed, but FG is what we're going to use in class. W is what I used to use when I was learning. I used that. I used an N for the normal force, but now we have to use Fn because that's just what they're accepting more recently. So we have to keep up with the times as well, okay? So hope your teachers are, sometimes the older teachers, they stick to like the older methods. For example, they'll use U for potential energy. That's not wrong. It's perfectly fine. In the science field, when we're working with it now in outside of school, we use the old proper symbols. But for your exams, again, you need to learn to encompass very specific habits when you answer these papers so that you don't lose marks on stupid things, okay? Because you want to maximize your marks. So the way it's going to work is that the way your papers are marked is going to be throughout the year because your teacher's marking it, and I'm sure they're very good at their jobs, but they're not trained to mark in the marking sense. Okay, those people, well, generally the idea is for you to get more marks there than you would in class. Okay, because that's what you're working towards. That's what we're doing. Okay, but obviously everything's correct, so it's fine. It's just some talking. Okay, that's fine. And then they say that. Okay, coefficient of kinetic friction. Okay, so mu k for both blocks. So what happened here? Equals 0.15, right? My notes. I'm not forgetting to tell you anything because I have a terrible memory. Not a very okay. So then mu k here, or the coefficient of kinetic friction, is also 0.15. So it's the same block. Okay. What is this coefficient? It tells us how much friction the block will experience against the surface, and it depends on the block and the surface interacting with each other. Okay. Now there's an equation for it, which you know. Anyway, moving on. So Newton's second. Now we're not done here, right? Because there's a bit more work for us to do before we can start answering. So you always separate the blocks because these are two different bodies, two different objects. Yes, they are acting in the same system, but when we are considering forces, we separate every body and work on it separately. So I'm going to call this A, sort of, or I'm going to say block, the 3 kilogram block, because that's what we can use that as like a title for it. So for the 3 kilogram block, I'm going to draw it here. Okay, 3 kilograms. Now I'm going to draw what's called a force diagram because that helps better than a free body diagram in terms of working things out. So I'm going to draw all the forces acting on this block. So up here is going to be my Fn, my normal force. Down here is going to be my weight, Fg, and you know that they're the same magnitude. This way you can see is going to be tension. So this tension, okay, it's going to pull this block there, and it's going to pull that block there, and it's going to be the same magnitude as well, okay? So I'm going to do that. And I'm going to write FT. So before in the days, we used to say just T, but now they want you to use FT, force of tension, which makes sense. They're just making it a little bit, I don't know, stuffy. And then on this side, because friction, okay, there is frictional force. So don't forget that. And that's FK. That's fine. You can use that symbol. Then for the for 1.5 kilogram block, we do the same thing. All right, so let's do it. Hope you are starting yours. You don't have to wait for me. I know I talk a lot. I do that on purpose to give you time to work in between, okay? Because we need to keep up the pace now, okay? You need to finish your paper 1 in under 2 hours, and then use the rest to just check and redo things carefully and look nicely. Maximum 2.5 hours. You should have minimum half an hour free at the end of your physics paper, okay? Chemistry, maybe 20 minutes free minimum. Okay, it's okay. You can go to 2 hours, 40 minutes because it is a little bit of a longer paper. But again, like 2 hours, 15 minutes, 2.5 hours, that's around the time you're going for. Maths, you're going for 2 hours paper 2 and 1.5 hours for paper 1. Those are the times you need to. I know it sounds very scary right now, but you'll see close in the year, once you do more of the sections, you get more practice, you master most of your work, that'll sound reasonable to you, and you'll actually aim for 80 minutes out of the three hours to finish your paper in, and that's what we're working towards. Okay, then you can really get all those marks and get confident in your own capabilities. All right, so 1.5 kilograms. Let's draw our block, and then all the forces acting on it. Now this is interesting. So the normal force is going to be up here. I'm going to leave that there for now. But going down, there's two forces acting downwards. Because this force is acting at an angle, there's going to be a, I'm going to do this in different color because I think it'll be better, maybe a pink. Okay. So this force here has a downward component, which we call the y component of the applied force. Okay. And this same force applied also has an x component going to the right. So we call that F applied x, okay, and it's a subscript on a subscript, but get used to it. So the x component, or the horizontal component of the force applied, going sideways basically, and then the vertical component of the applied force, which is acting at an angle. So the vertical component of the y component, okay, basically up and down, that's the vertical component. Left and right is the horizontal component, x. These are the symbols you need to get used to using. I know some people use this thing where they say f parallel and then f perpendicular. This is what I used to use in school also, but don't, okay, because it's not right. This is what I was using when I was learning it because it helps put things together. But by grade 12, you should be using the proper symbols, which is y and x for horizontal and vertical. Okay, it's these small things I'm telling you that there are exam skills that you need to know, little tiny habits that you need to sort of enforce. So exactly how we're doing this. This is how you. I know it sounds like there's not a lot of room for creativity, but there is. Okay, there's a lot of different ways to answer the questions. But what I want you to get right is the notation. Notation is so important. It's like a language in its own because it's the way that you express the subject, the science, in this notation, and the notation is very specific. So as long as you get that right, you can be as creative as you like with your answers, as long as your notation is correct and you're obeying all the laws of maths and science. Moving on, again, I'm talking a lot and I'm sorry, but they're very relevant things, I think. So this is 1.5 kilos. I always like writing the mass in there. And then we also have the weight of it, isn't it? The weight didn't go anywhere. The weight is still here. So the weight is now Fg, which is equal to mg, and Fn is actually equal to. Was someone saying something? Okay, sorry, I thought I had someone put their mic on. So the normal force, what is the normal force going to be? Can anyone guess, like in terms of the weight and stuff like that? Like here, Fn is just equal to Fg, okay? We know that. But over here, it's not. Fn is equal to the y component of that applied force plus the weight. Because what is normal force? The normal force is the reaction force of the block pushing down on the surface. So it's the reaction force of the surface pushing back up on the block. So whatever the surface is pushing back up on the block will be exactly what the block is pushing down on the surface. I hope you understand that. So in the normal case, the 1.5 kilogram weight, that weight is pushing down on the surface. but there is also an applied force which is further pushing the block down on the surface. So there are two forces that are pushing the block down on the surface. So there is a greater force that the surface will apply on the block because of Newton's third law. Okay, hope we're clear on that. That's a very important point. And that's everything here except for friction, which goes there. Oh, and the tension. And then the tension was in red, wasn't it? Let's just keep with that kind of theme. And then that's FT. These are all free body diagrams, and they are going to help us a lot. Okay, let's move on. I'm writing too big. Now, after you've done this, it shouldn't take you long. This should take you 3 minutes, maybe 2, and then you start answering. Okay, obviously you're going to get used to it, and the only way that you can do that is through practice. No other way. Okay, you can't just wake up, do this one time, and then say, okay, I'm going to write my exam. I'll be fine. You have to be doing it dozens of times throughout the year in order to, for when you get to the exam, it becomes muscle memory, and then you just start doing your answers very quickly, and that's what we want. Okay, that's what we're working for. So 2.1, what is Newton's second law in motion? It's a very long one, but I'll give you some time to write it down. I hope you know it from the top of your head. If you don't, that's fine. Newton's second law, you can use the momentum version. They sometimes accept it, but I think it'll be safer for you to use the normal long version, okay? Which is when a force is applied on an object, the object will accelerate in the direction of that force, and the acceleration will be directly proportional to the force applied. Okay, and inversely proportional to the mass. I'll write it with you, then we can do it together. So yeah, if I can do it, you should be doing it also, okay? Don't be lazy. So when a force, a net external force, yeah, resultant is better, resultant. So I still remember this definition from grade 11, okay? That's because of all the training, because I've been doing this so many times. I must have answered, but like 2,000 past papers. So, and not just once off, again and again and again for practice. That's what you have to do. And I know this from just because I've done it. We didn't do these things again in uni. It's just, this is all from high school. So if I can do it, you can too. Acceleration. The only difference between you and I right now, we both did the same subject in school. We had the same access to past papers. The only difference is the experience. I just have more experience because I've already done it, and I've been doing physics a lot. That's the only difference. So my role here is to teach you and to help you so that your experience, and when you get your experience, you can do it in a more efficient way from what I learned. Okay. Acceleration. I'm not sure how to spell acceleration to this day. I think it's 1C and 2 L's. I think so. I don't know. 1C, 2 L's. Acceleration. Yeah, that should be fine. It's fine. Object will accelerate. Oops. Accelerate in the direction of the force with a magnitude of acceleration. Whatever that is, acceleration that is directly proportional to the force applied and inversely proportional. Don't say indirectly proportional, that's wrong, because an indirect proportion is still a proportion, just it's not an inverse proportion. So it's not the same thing as an inverse proportion. Inverse proportion means 1 over k equals, 1 over k is proportionate to x. So x is inversely proportional to k is inversely proportional to x. That's what that means. X is proportional, directly proportional to k. If x increases, k increases, that's fine. But there's no symbol for indirectly proportional. That's not a thing. It's not. Some people say that. Please don't use that. Yeah, that's wrong. So inversely. Sure, I said it like that. Inversely proportional. It's a bit tedious, but yeah, you've got to do it. for 2 marks, right? 2 marks is a lot. For free, these are free marks. Your definitions are all free marks. Make sure you don't lose those 2 marks, okay, please. To the mass of the body. Okay, cool. My writing used to be better in high school, I promise. So let's move on. Okay. 2.2. Calculate the magnitude of the kinetic frictional force acting on the 3 kilogram block. So let's go to our 3 kilogram block. Okay, so there's a frictional force, and we need, okay, our equation for frictional force. We know that the coefficient of kinetic friction, mu k, that's a Greek symbol mu or micro, and k, but in this case it means coefficient of. So coefficient of friction is equal to the magnitude of the frictional force divided by the normal force. Okay, it's the ratio. That's why it doesn't have units. I hope you know that. You can ask that as well in multiple choice. The reason that this doesn't have units, and they'll put an option there because these 2 units are both forces and they cancel. That doesn't make any sense. The reason this doesn't have units is because it's a ratio. Ratios do not have units inherently. Okay, so let's we want to solve for Fk. That's what the question is asking us. Let's do that. Fk is equal to mu k times n. Mu k they gave us as 0.15, but I'm going to leave it as mu k for now because we need one more step. And mu k normal force is mg. So yeah, now we can substitute. Mu k was 0.15 times mass was 3 kilograms, gravity 9.8. Put this into your calculator, please. Do it with me. If you get a different answer, please let me know. 0.15 times. Oh yeah, that's the other thing. You don't have to put a 0 into your calculator if you're doing a decimal. You just put the dot at the bottom, just point, and then 1.5, it does the same thing. So again, short tricks like that to save time. I'll also show you how to use the times 10 to the x key if you don't know yet. And yeah, that's later in the year when we do electrostatics. So 0.15 times 3 times 9.8. And that's 4. And also don't overdo the brackets, please. I know some kids, they put one bracket in between every multiplication. Your calculator is sharp. Your calculator is sharper than you, okay? It knows how to do these things. You don't have to worry. As long as you put the thing in there, your calculator can do BODMAS, okay? It can. No, it'll be fine. Just put the multiplication symbol and you're good to go. You don't need to bracket everything and waste time unless you absolutely need to, unless there's going to be a discrepancy. But obviously you need to use your basic awareness of maths for that. So don't overdo to the brackets. These short, simple things can really get you a lot of time, and time gets you marks. Remember that. Time is directly proportional to marks. So 0.15 times 3 times 9.8, I'm getting 4.41 newtons. Okay, so whatever we have, let's put on our diagram. Okay, you know how we work. Anything you find, you put on the diagram. Put it on the diagram, 4.41. Okay, yay, now we know something. And we know that this is going to be, well, we don't need that value really, so it's fine. Now moving on to 2.3, draw a labeled free body diagram showing all the forces acting on the 1.5 kilogram block. So this is that. And essentially, yeah, so now we convert this into a free body diagram. How do we do that? We just replace the this block with a dot, and then you're sorted. Okay. Now there are 2 ways to do this free body diagram. Show the first one. Make sure you show all the forces. Okay. So that's your body. We know that there's normal force going to be up there. The normal force must look like it's bigger. Make sure you do label it, please. It must look bigger than each of the individual forces going down. Okay, you must show the proportion. I said it's the same thing with the graphs of motion. Please show, it doesn't have to be accurate, you don't have to measure the vectors. As long as it's seemingly proportionate, that's fine. So here is FG, and then here is FY. This is the one method. Then here is going to be the FX. Here we have 2 things. We have FK and we have FT. Okay. Cool, right? So this is one version. I'm not sure if this is correct. Okay, you can show the components of the force applied. But I think this might be easier for you to do, to just show it as it's drawn in the diagram given, okay, where the force is just acting. Now, we generally draw, the rule is to draw the head of the arrow away from the body, like so, okay? And this becomes your, oh my God, my arrowheads are shameful. This becomes the force applied, okay? And then here, you need to show the angle. You can show 30 degrees there, you can show 60 degrees here. I'm not going to baby you about the trig, okay? You've been doing it for so long now. And this way goes there's nothing there basically. Oops. And up is the normal force, Fn, arrowhead, very important. And you must show it touching to the circle. Okay, if you don't show everything, you can make a big circle and color it in, that's fine, as long as all your arrows are touching it. If not, you can lose marks, okay? They're very particular about these things. Okay, big circle, right? That's fine. Going down, I'm going to do my FG. So see, like this, doesn't look too nice, okay? But it must be proportionate. I'm going to make this one a little bit shorter, like that. That should be fine. FG. And then here is two things. We've got FK and FT. Okay, so yeah, so this one you might like more. I don't know. I've seen recently, well, not recently, but like 2017, 2015, they accepted when you did that. Now, in the actual science field, if you do tertiary physics, this is not correct. We don't do this. So a free body diagram generally has the tail starting at the dot and then moving the head moving away from it. That's how it works. Okay, so you don't want to have a case where you have a really strict examiner for you this year who is very, very into the science field and has lots of physics education, which most of them are PhD holders. So, and then they're fussy and they're like, no, this is the correct science. We're not going to accept this nonsense. They could very well do that. So please do stick to the correct thing, which is what I showed you. Okay. Yay. Moving on. Isn't physics fun? Yay. Okay. Moving on. That's another 3 marks. Oh, 5 marks. Look, you're getting marks for basically nothing. How cool is that? Oh, don't forget that angle. You must show it, please. Please, please, please show that angle. Don't just, yeah, thank you. 2.4.1. Calculate the kinetic frictional force acting on the 1.5 kilogram block. So you start with your equation. Mu k is a ratio of the kinetic frictional force and the normal force of the object. And we just subject change to get it in terms of frictional force because it's just easier to work with an equation that's more linear, which is mu k times n. Now mu k, n in this case, though, we said was equal to the weight plus the y components of the applied force, yeah? So the y components of the applied force we'll talk about now, but mu k it stays the same. Fg is just mg. And this here, let's see how we do that. So this is our force, okay? That way, the hypotenuse, 25 newtons. Then the perpendicular component goes like that, with the vertical component, that's Fay. And the horizontal component goes like that, and that's Fax. 90 degrees here, 30 degrees here, 60 degrees there. You don't need to use the 60, some extra people do. Please don't be extra, save yourself some time. And now it's basic grade 10 trigonometry. Yay, okay, this is child's play at this point, all right? So physics is just made of a lot of tiny, simple things. You just need to put them all together and you'll be fine. So how do we're trying to find Fay. We have the hypotenuse and we're using this as our reference angle. That's opposite to the hypotenuse. So opposite, you know what that is, sine. Okay, so sine 30 degrees times Fa is equal to Fay. That's our equation because trigonometric. I'm not going to explain that to you. Unless you want me to, I will, but I don't think I have to. I hope I don't have to because that would be quite sad. So this is just going to be Fa sine, and I'm going to put theta there because this is just the equation. Substitution, very important, 0.15 stays the same. Yeah, you can put brackets, you know why? Because it's 2 separate terms, okay? Multiplication is distributive, but it's easier to write it like this. M is 9.8 times G is, G is 9.8, M is 1.5. That's the order doesn't matter. Multiplication is commutative. Don't worry about it. And again, this is what I'm talking about. So some people who do on square bracket here, they'll put small brackets like this, and then they'll put, don't do that. Please don't be extra. Just, this is fine. And this you can write as one single term. You don't need to say Fa times sine. There's no, the notation for maths is to just write 36 cos of 75. You don't have to put a multiplication symbol in between. It's assumed. Don't do stupid things, please. And the F, okay, I'm not using that one. Fa was 25 newtons. Oh no, there's a plus sign that goes there. Plus 25 sine 30 degrees. This put into your calculator as you wrote it. Okay, there's no need to be excessive with your brackets. As you wrote it, you can type it in. So 0.15, big bracket, 9.8 x 1.5 plus 25, the sign key, and then 30. Then you close that sign bracket, and then you close your big bracket. So remember, there's a small bracket in here for the 30 on your calculator. Please close it because sometimes it can get a bit weird. And then equals 2. I hope you get the same thing I am. I'm getting 4.08 newtons. Okay, let's put that onto our diagram. How are we looking for time? I was over explaining a few things. Okay, not bad. No, we're doing okay. We're doing fine. We will finish this paper, and then you can sort of see how your exam answering skills are. The next week will be full-blown application again. We're going to be doing work energy and power and organic chemistry, everybody's favorite. Organic chemistry is actually very fun, guys. Okay, I know people have been telling you otherwise. If you should listen to them, don't listen to me. It's fun. I don't want you to get preconceptions and then you already start doing badly just because you said I'm going to do badly. Don't do that. Organic chemistry is fun. It's new, but it's exciting. It is a new language, but it's simple. It's basic. Your organic chemistry syllabus in high school is absolutely basic. You don't get into um, biochemical molecules or anything like that. It's absolutely basic. There's no industrial application, just simple, straightforward, simple reactions. There's only a few of them that can be tested in your exam, and I will show you what they are. And outside of that, they can't test you. So the mistake that school teachers make often is that they teach it generally. They teach a general organic chemistry, which is fine. It's okay. That's what they're supposed to be doing. But then that's where you think that, oh, the whole world is open to be tested in your exam. You start getting scared. You don't study it. You leave it out because you say they can ask me anything. Oh, I'm going to die. So don't do that. So I'm going to show you that they do have limitations. Your examiners can only test you a certain types of molecules reacting with certain other types of molecules, and they're very few. There's like 4 different types of addition reactions and only 3 types of substitution and things like that that they can possibly ask you. So I'll show you those things, and then I'll tell you this is all you have to learn. Know it like this, but know how to change things up if you need to. But they can't ask you other molecules. Okay, so it's going to be simple. Just go in trusting me. Okay, you'll be fine. Organic is good, and it's my section because medicine we do a lot of biochemistry, so it's yeah, you'll be fine. This I haven't done in a while. We only did one semester of physics, but we did all the physics we'll ever need, so it's a bit hectic. But yeah, moving on with this, forces are the easiest kind of physics you'll get. It gets very weird if you do things like capacitance and all of that. 2.4.2, tension in the core. That was tension. I told you they have to ask something about tension. So what do we do whenever you see tension? Don't get scared and say 5 marks. What am I going to do? I did nothing. No, this is the equation you use. FR is equal to MA, and that's it. That's all you do. Do this for each block, and you're sorted. Okay. Now we're going to say FR in the x-axis equals MA in the x dimension for the first time we write it because it's more correct. You won't see this in the memo, but do this please. It's a very good thing to do because it establishes you're not talking about all the resultant forces. It's just in the horizontal plane, left and right, side to side. That's all we need to think about because we're on a horizontal surface. All right, we're not floating around in space. Now let's go for it. Okay, tension in the cord connecting 2 blocks. We just set up equations for both sides. I know we don't know what the acceleration is. Don't get scared and say, oh, I don't know what this acceleration is. I can't answer the question. Leave it out. You lost 5 marks. Don't do that. Even though you can't see, again, you can't see marks 8, 9, 10. Focus on marks 1, 2, 3. Okay, what can you get? I can write this equation, you get a mark for that. I can substitute into this equation, you get marks for that. I can substitute into that substitution with values, you get marks for that. Already you can get 3 marks out of the 5. You see, even if you don't know how to get the final answer. Don't leave things blank, please. So let's sum up all the forces now x direction for block, the 3 kilogram block. Oh, here we go. So it's only going to be friction and tension. That's all. There's nothing else acting side to side. There's nothing else pushing the block in either direction. Let's go for it. Okay. I hope you're working ahead of me, please. Something I was going to tell you here. No, we're fine. Okay, we can move on. Can we? Yes, we can. Okay, so it's friction. Let's draw the tension first. Because tension is going in the positive direction. For forces, generally only right is positive. You don't need to be too complicated about that. So tension minus Ft, sorry, Ft minus Fk is equal to M and then A. Okay, I'm not putting the arrow here because I'm substituting the value A in place of the x, the horizontal component of its horizontal acceleration. So there's no need to, and I've already established it's a vector in this initial substitution, my statement. So I can just put an A there and say I'm calling my horizontal acceleration vector A. Okay, we don't know what that is, so that substitution is fine. There's no need to be vector specific when you do the rest. Okay, it's just good physics to do it in the first part. We can substitute for tension, right? What is it? We don't know. Well, here actually at this point you can substitute a T for tension if you like, if that makes things a bit easier. And then Fk, we know Fk, right? We found Fk. It was 4 point something, 4.41. All right. 4.41 is equal to the mass of our first block, 3 times A. And this becomes equation 1. Okay. Now equation 2, we write again, Frx is equal to MAX. Okay. Fr of this one, now there's quite a few forces acting on here. Let's have a look. 3, okay, there's the horizontal component of my force applied. There's the frictional force, and there's my tension. All right. So let's substitute that in there. Hope you're following, using your diagram also to do this. So the only thing that was moving in the positive direction was the horizontal component of our applied force, sorry, FAX minus FT minus Fk. This is going to equal mass times acceleration. Substituting for FAX, what is this going to be? It's just going to be FA 25 cos 30. Okay, we know that because FAY was 25 sine 30. So obviously it doesn't take a rocket scientist to understand that aspect. So don't freak out about it. If you want me to explain it to you, I can. It's also in the notes. But I think we are good. So substituting for FAX, we know it's going to be FA, which is 25 cos 30 degrees. FT, we don't know. I'm just going to put a big T. Friction, we did know it as 4.08. Oh, it's right there, staring at my face. So 4.08. Mass is 1.5, and acceleration is yet unknown. So there are a few ways of going about this mathematically. You can, I don't know, subtract them from each other. You can do all kinds of funny things. But what's looking easy for me right now is to just multiply everything by 2. So I'm just going to get, okay, but that's before we do that, let's simplify first. Let's simplification. Okay, it's nice to have just one add up all of our like terms. Sorry, I might be talking a bit too fast. Let me know if you need me to slow down, please. I don't want to be rushing and then leaving you behind. Let me know if you need me to slow down. The way that I'm doing things, I'm assuming that you're keeping up at this pace. If you're not, let me know. I can slow down. This is just what I'm used to. And if you're keeping up, great. If you're not, do tell me, please, because I am doing this for you, okay, not for me. So 25 cos 30 is, oh, I don't need to do that. I'm just going to put 25 cos 30 minus 4.08 and see what happens. 25 cos 30 minus 4.08. Hope we get the same thing. I'm getting 17.57 minus t is equal to 1.5 times a. Now I'm going to multiply both sides by 2. 17.57 times 2 is 35.14 minus 2t, that's important, is equal to 3a. Now why I said this is easy, because if we have 3a on both sides, we can just equate this part, okay? So that's what I'm going to do. This is now equation, we already called it equation 2, that's fine. And so we can just equate both left-hand sides. So t minus 4.41 is equal to, I hope you understand the maths here, 35.14 minus 2t. All right, so I want my t's on the right, so I'm going to move this 2t over here. This is going to become 3t, okay, equals 35.14 plus, I'm going to write it down, 35.14 plus 4.41. Don't like working with numbers. Plus 4.41, they get very confusing. It's why I never did counting. 39.55. I prefer just clean pure maths, which is just variables, 3t, and calculus. Calculus, it's amazing. 39.55 divided by 3, and we get 13.18. Is that correct? I did answer this before, yeah. 13.18 newtons. Ta-da! Okay, that's 5 marks. So there's 2 here, 1 here, finished. And then you're done. That's how you get 18 marks. I know it took a while, but I was explaining. So you should be able to finish this in maybe 15 minutes. Yeah, 10 by the end of the year, because Newton's laws is something straightforward for you. This question, I'm sure we're familiar with things like this all the time. I mean, we did so much kinematics, a lot of kinematics actually, so everything's just going to be revision for you now. So I hope you can work ahead of me in this. Now, question 3, and I want you to start on a new page, please. You always do a new question on a new page. Don't ever, yeah, that's proper training for the exams. New page, new question, new page. That's the rule. Okay. Taking my time to do this because it's an important thing to do. For a lot of reasons, in case you need to come back and change things, that you have a good chunk of space left and things like that. You know, for English, for your English papers, when you're answering your comprehensions, after every answer, you need to leave 3 whole lines. 5, I used to leave 5 in case you need to come back and change, because otherwise you don't have space and there's a lot of explaining to do. So yeah, I'll talk to you about that in a few. And we'll start with NBT preparations by around March, April. It's just going to be like one question, 1 or 2 questions at the end of the lesson that I'm going to show you guys, and it'll be nice. It's, yeah, have a little like compilation for you. As long as you, yeah, I'll show you how to think for it, because that's the more important thing. Okay. Question 3, is somebody messaging me about it? Oh, okay. Back in the lobby. Okay. Oh, oops, my Teams is open on Chrome. Okay, I'm going to add. Can I add you? No, I don't. I think I have to do it from my side. Okay. Sorry. Participants, there go. Okay, I can't see the lobby from here. Let's go into my laptop, phone, rather. Okay, guests are waiting in the lobby. And Ralph, admit. Okay, hi Ralph, sorry about that. Let's see, what did we do so far? Okay, I didn't really start. I just said how important it is to leave space, and like for English and stuff, you should leave 3 to 5 lines after every answer and come back to it. English was, yeah, I got a 90 for English because it took a lot, and I really wanted that because, well, a friend once told me that you can either be a maths person or an English person, not both, and I wanted to prove them wrong, so I did both. And anyway, yeah, so with English, it's just a lot of, again, how do you answer these questions? You'll find that that's my trick, is how do I answer these questions? How do I get into the head of the examiner and really dissect what they want from me specifically? And there are a few good resources you can use for that I'll show you later in the year. But that's the question. So don't just go jump in. I know they say English is your home language. You don't really need to study for it. Yes, you do. You do, actually. You need to figure out and learn and sit with yourself and with those question papers and look at the memos, look at the question paper, look at your answers, and compare and see what they're looking for and what they want from you. And English is an open memo, so that doesn't mean you write whatever. It means you write your any answer you put is fine as long as you can motivate correctly within the language learning objectives. So as long as you motivate why you think a certain thing is like this, you should get all the marks. Again, you answer the question in full, and you know the difference between discuss and critically discuss and analyze and compare, contrast, those kinds of things. Sorry, I'm going a bit off topic, but it's all relevant. It's all relevant, guys. Okay. So again, if you just jump into 3.1, you deserve 1 to what happens, because again, you always, I'm a pacifist, don't worry, start with a schematic, okay? And this is our general case where just something is falling. There's nothing crazy here. Object falling to the ground, there's going to be a final velocity. There's going to be an initial velocity of 0 because it is falling to the ground. It is dropping from rest. There's going to be acceleration. Back in the days, they used to actually test air resistance. So you guys are quite fortunate, like not in my times either, but like way, ago, they used to test air resistance. So yeah, that's so nice here. Acceleration is always 9.8 meters per second. Change in time is unknown, and we know that change in y is 20 meters. Cool. So we have 3 things, which means we can solve for any other thing. That's the criteria. Let's look at what they want from us. 3.1. So the term free fall, there are 2 accepted definitions for this. You can use either one. You can use either a motion in which the only a motion under which the only influence is gravity, or where gravity is the only influence on a falling body. So it's a motion on which, in which, whatever, in which the only why is battery saver? Just trying to get the phrasing because they're very particular about these things. I'm going to look it up on our doc. Motion with which, not on which, motion for where the only force acting is gravity. So when something is falling and only gravity is acting on it, that's free fall. Where is my VPM? Kinematics. There we go. There we go. So definition that. There we go. Motion during which the only force acting on the object is gravitational force. Okay. Motion during which the only force acting is gravitational force. Hope you learned your definitions. What I used to do is make little flashcards for only the definitions for physics and chem. You just write the definition on one side, the explanation on the other side, and you look at it. You don't learn it, you don't study it, you don't stand in front of the mirror and recite it 1,000 times. Those are inefficient learning methods. This is a passive learning method and very strong. So you take the cards and then you shuffle it. You take the card, you look at it, you ask yourself, do I know the definition first? Do I know what's in the back of the card? And you turn it around, and if you do, you put it in one side. If you don't, you put it in a different pile. Okay, so you sort these cards. You keep sorting it, and you keep. And I know at first, obviously, you're not going to know everything, so everything's going to go in the same pile. But then you do it again, and you look at it, and by the third time you look at it, and there will be things that you already know in your head, like okay, this is free fall. Now I know the back of this card is going to say a motion during which the only force acting is gravitational force. You turn it around, you're correct. You put it in a different pile, right? And you can hold it in the same hand. You don't have to like make actual physical piles. And then you take the next card and you see, this says inertia. I don't really remember what inertia is. So you turn it around, you read the definition, and you put it in a different pile, which is I don't know. And you keep doing that. And eventually, the pile for don't know gets smaller and smaller and smaller and smaller. The pile for do know, you manage to predict exactly what's in the back of that card, gets higher and higher and higher and higher. This is called a passive learning flashcard technique. It works very well. Please try it if you want to. There are digital online things that you can use with flashcards. Let me see. I can show you Anki. So this is a very common thing with med students because you have to memorize large amounts of information. So it can also help with high school work. Let's see if it loads. I don't use it too much because I prefer taking notes. But yeah, so shouldn't take long. Okay. So if I'm looking at, for example, human biology, and I want to do that, and just accessory organs, or like this is the digestive system. So I say, okay, this was easy. I know all of those things. What is chemical digestion? I know what that is. Easy. What is, okay, it's a bit, yeah. So say I don't know this. Hard. So it shows it to you later. Basic function of the digestive system to break down things and stuff like that. So you can keep doing that, and then with all kinds of topics, and yeah, that's Anki. But you have to make these. Obviously, that takes a bit of time. If you go to text, it's something that's more something. Okay, anyway, that's fine. So that's basically Anki. It's like an online flashcard thing. You can do it on your phone. Motion during which the only force acting is gravity. Let's answer the question. Okay, so this is how we set it up. Basic, right? Nothing crazy. 3.2.1. Speed at which the ball hits the ground. Obviously, we just set up an equation. You should be flying at this now because we've done so many examples. Which equation goes here? I'm sure you're thinking about it without needing to look at one. I hope so. You can look at one if you have. I sent this in the group. All the equations are there. I hope you're not, but okay, maybe by April you won't need to think about it. So this equation, we're going to use the one without time. we're going to use the VF squared one. VF squared is equal to VI squared plus 2A change in Y. Again, don't put change in X because X refers to horizontal displacement, and this is our frame of reference, okay? Where this is Y, this is X. We're not shifting our frame of reference, so remember that. VF squared is what we're solving for, so we can leave it, and then we can say VI squared is 0, let's square it, and we can say that's 0, plus 2 into 9.8 into 20, because Y is given, all right? Here's the question, sorry. Okay, so then VF is just going to be the square root of 2 times 20 times 9.8. Listen to your calculator quickly, because the things that you can do fast, so you don't need to take your time for it. Square root 20 times 2 times 9.8, and I'm getting, oops, 19.8, okay? 19.8. There's no reason to put 19.80. It's the same thing, guys. Don't waste time. That you'll use when you're working with significant figures in higher physics. You don't need to worry about that right now. And don't say 80, it's 19.80. Or if it's, okay, yeah, that's the other thing with fractions. So 3.14 is not 3.14, it's 3.14 because it's diminutive. It gets smaller and smaller as you go. This is not a teen number. It's not after 10. It's a decimal. So you just call the numbers out. You don't say 14. You don't say 7.35. It's 7.35. Okay, that's I know it doesn't make much of a difference, but that's just the correct maths. Okay, you don't, yeah, because there's specific names that the teens are for numbers bigger than 10, smaller than 20, not decimals, which, yeah, because you're not calling out a whole number after the decimal point. They're just a fraction, a part of something. It doesn't have the 10 in it. So yeah, a lot of people don't get that. Even grown-ass people sometimes. It's humiliating. Anyway, 19.8, what's the units here? Meters per second negative 1. Do they want magnitude only? Speed, yeah. So speed says you don't need to say which direction. It's fine. The time it takes for the ball to reach the ground, another simple thing. You should hope the equation is clicking in your head. We're solving for time. You can use the long equation, but let's use a shorter one, please, because again, time. 3.2.2. I'm going to use VF is equal to VI plus a change in time. All right. VF, we know what is VF. VF is, oh, I forgot to put it down here, sorry. 19.8. Always put stuff on your diagram, meters per second, negative 1. Notice I'm not leaving out units anywhere. That's just good habits, okay? VI is 0. So 0. But, oh, sorry, we know this one, 19.8. And change in time times acceleration is just going to be 9.8 change in time. Substituting here, basic, absolutely simple. Time is equal to 19.8 divided by 9.8. Substitute that, please, and I hope you get the same thing I do. If you don't, let me know. 19.8 divided by 9.8. 2.02. Okay, 2.02. Yeah, because like if it was 2.202, what are you going to say? 2.202. That doesn't make sense either. Sorry, just. Then what are you going to say for pi? Oh my god, pi is 3.14159265358979246. Yeah, I just know this for no reason. What are you going to call this? 3.1 gajillion 4 septillion? No, it's 3.1415. Yeah, okay. So that's my point made. I hope you believe me now. Sorry. I'm using my position of influence to convince you to do the correct things. 3.3 sketch of velocity time graph. Absolutely basic. This was a very simple question. I hope you agree. With no values, but we're going to put values because it's just good practice, okay? And they don't often ask you like this. So we're going to do for the training. You know what we do? We first say heading, okay? Velocity versus time. Then we draw a system of axes. We say time measured in seconds. We put our arrows to indicate the continuation of our axes to infinities. Velocity measured in meters. We put a 0 there. That's how we set it up. Now we're going to look at the motion of the ball. The ball was just increasing from 0 to a much higher. It was moving faster. You can imagine that, the ball that you let go from a 20-meter building, right, a really high building, and you let it go and the ball is falling. Now when you let it go, you're dropping it, so it doesn't have any velocity. It's velocity-less, okay? And as it falls, it gets faster and faster and faster because of gravity pulling on it at an acceleration, at a rate of change of velocity. And so it's going to end with a much higher velocity. So that's why velocity increases when you drop something. So that's going to look like that. But for the case of our axes, I want to make it look a bit nicer. So I'm going to do that. And I'm going to say that this is 19.8, and this time is, there's no arrow there, but it's fine, 2.02 seconds. All right, and that's how you get all your marks in this question. It was a very easy question, but I hope you didn't have any issues. If you do, again, I ask my grade 10s all the time. I stop and I ask them, anyone want to say anything? Because I know that they're shy, okay? And I'm expecting you guys to have gotten over the bulk of your social anxiety and to know when you need help, okay? So I'm not going to stop every 5 minutes and ask you, are you okay with this? Can I move on? Are you fine? So let me know. All right, don't just be quiet. Let me know if you need me to stop or redo something. I will, because this is important. Next question. Again, you page break. I'm going to do a dot line here. Next page. And question 4, momentum. How are we doing for time now? Because I have my grade 10s at 6 to 8. That's fine. They can wait a bit. It's fine. It's just grade 10 stuff. It's nothing major. I mean, I'm joking, of course. It's very important. Graph below shows, etc. Blah 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 blah. Okay, so this is a graph, kind of cool. Let's understand the graph a bit. Okay. So they're talking about a car, and this is car A. It's a bit weird. It has momentum and it has time axes. Okay, so it's indicating that at this point here, at 30,000 kilogram meters per second, was what it started with before the collision. Okay, after the collision, it was down to 14,000 kilogram meters per second of momentum. And that change in momentum is obviously going to be 14,000 minus 30,000, isn't it? And this represents the collision time because the momentum is still changing. Okay, that's another interesting point in physics. When a collision is happening, momentum is inconstant. Momentum is changing. So you will get a tangent. You will get a curve, a slope rather. And the collision time, as you can see, is 0.1 seconds. Okay, can you see that? 20.1 to 20.2. Yeah, 0.1 seconds. Pretty cool. And they gave you this because they think you're stupid. You don't know where's north, south, east, and west. Anyway, what do you understand by the term isolated system as used in physics? An isolated system, again, there are two definitions here. But we're not going to do that because we need to do a schematic. Okay, so we're going to say before. We're going to say after. And what exactly is happening? A car of mass 1,500 kilograms. I'm going to draw a car. It's going to be a very nice looking car for those of you who like cars. Sorry, it's going to be an abomination of a car. So just basic grade 1 kind of drawing. And this is A. And then for B, I'm going to draw another more rounded car. Yeah, like when, Mr. Bean kind of type vibes. I don't know. Okay, and then that works. So it's fancy sports car. I don't know. So B is 900 kilograms. And A is 1,500. A is moving this way. Do we know how fast? 15 meters west. Okay, so west is that way. And this is for B. Okay, sorry. For A, we don't know. So just V. B is moving that way. Yeah, we should kind of figure it because if they collided, V is equal to 15 meters per second. Negative 15 meters per second. That's important. Then they collide. And afterwards, we don't really know anything about afterwards. So I'm going to draw the cars again. You can just draw boxes. That's fine also because that's how we train, okay? A, weight stay the same. Velocity will probably keep going that way. Do we know the velocity afterwards? Not really, but we know the momentum afterwards, right? Remember that? And that's kind of cool. That makes this question slightly different, but interesting, right? And yeah, so 900. And then 15 meters, and then we don't know how fast it is moving after the collision. So V. Okay, so that's set up. We don't need to do anything else right now. That's just the schematic. Now we can answer the questions. 4.1. What is an isolated system in physics? Is a system where the net external force is 0. Or you can say a system that excludes external forces. Okay, the second one is a newer sort of one that they included in the memo recently, if I'm not mistaken, 2015 for the supplementary paper. But they have carried it on so far, but I think it's safer to go with the first one because that sounds more like what they would want from you. So a system in which the net external force is 0, or the system that excludes external forces. Actually, no, it's fine. Learn the simpler one, okay? It's the same thing really. There's a reason they included it. A system that excludes external forces is an isolated system. Use the graph to answer the following questions. Let's do that quickly. So there's only one question left, okay? And then we're done. I hope you would have learned something. Okay. Calculate the magnitude of car A just before the collision, so 4.1. And also tell me if you have any tests or assessments or practicals or whatever coming up. I can try and help you guys with that. Okay, that's what I'm here for. I am busy, but I'm doing this too, so I'm kind of committed. So let me know if you need extra help, extra resources, you don't understand a question, you don't understand the scope, or whatever the case is, okay? 4.2.1, sorry about this. I wasn't thinking and I was writing. Magnitude of the velocity of car A just before the collision, right? How do we do that? We know the mass of car A, we're finding the velocity, we know the momentum of car A before the collision. Okay, that's why interpretation of graphs is so important. This is the magnitude of the momentum. Some kids would not have understood this, and just not knowing what to do, they're trying to use energy principles and all kinds of weird things. Okay, let's start. 4.2.1 magnitude of car A, so P is equal to mv. Okay, P is 30,000, mass is 1,500, V is V. So V is equal to 30,000 divided by 1,500, and we get an answer for that. Let's substitute. Calculator please. 30,000 times 1,500, and I'm getting a pretty divided, sorry, 31 to 3, 30,000 divided by 1,500. Okay, 20. Is that right? Yeah, 20 meters per second. Okay, they just wanted the magnitude, so we don't have to put direction. Okay, 4.2.2. Velocity of car B just before the collision. Now you can see 5 marks, so you know what they want. They want us to use the principle of linear momentum, of conservation of linear momentum. How do we do that? We say sum of the momenta before the collision equals exactly the sum of the momenta after the collision. And you know what we do here? We'll say mv1 plus mv2 is equal to mv3 plus mv4. Now for mv1, which is the momentum for car A, we know that it's 30,000, so let's just write the momentum. There's no need to multiply, that's just being stupid. So 30,000 plus mv2. We don't know the momentum of car B because this is only for car A, but do we know anything else? Yes, we kind of know its speed, we know its mass as well, and those are the things that are important. So times 900, which is the mass. You can use your diagram. I know I'm not going up for scrolling up to it. And negative 115. Okay, negative 15, because it's not a 0.5, it's a 15. Negative because it's moving west, okay, opposing the direction of motion, opposing the positive direction. Here, mv2, yes, we know the momentum after the collision of car A, 14,000. And do we know the momentum of car B after the collision? And that's what we're trying to find. So the mass stayed the same, velocity is what we're finding, v4. All right. Now substitute, put all of this here in the calculator, and then I just want the 9,900. I just want the 900v on the right. Okay, so give me an answer for that. You don't have to tell me, but I put it down. The reason I'm not asking you to give me answers is because I want you to sort of get learning autonomy. You need to do things on your own. Okay, so that helps, so that you know that you can in the exam. Everything's just up to you. You're allowed to make up equations, not make up formulas, but make up equations from the formulas and substitute into them properly. All right, so let's go for it. Right, we're running out of time. 30,000 momentum is simple. Let's not stay too long on this. Minus 15 times 900 minus 14,000. Okay. I have 2,500. Is that correct? No, that's not looking correct. Let's try again. 30,000 minus. Okay, we'll try it again. Okay, I'm getting 2,500. Tell me if you get something else, okay? 2,500 equals 900 times V4. So V4 is equal to 2,500 divided by 900, and that should give us a nice answer. Right, I'm getting 2.78 meters per second. Magnitude, they wanted the velocity. So if you don't put the direction here, you will get, your marks are going to be, you're going to get 4 out of 5. Okay, and you don't want that happening because you did all of this calculation perfectly. Okay, so please say 2.78 meters per second east. Okay, it doesn't take much. This word east, even if you just put one e there to say that way, that's it. 1 mark. Okay, so don't lose, and marks are so precious, guys, so precious. And last question, yeah. Okay, so 4.2.3 is simple. Read it, please, and get started. I'm going to give you a small head start here just to see if you know what you're doing. Okay, so you have the question, you know all the information. Let me just show it to you again. You just need the graph, actually. You have all your calculations on your page. Think about it, get a start, see how far you go, see if you have an idea of what to do. Again, don't focus on marks 8, 9, 10, focus on marks 1, 2, 3. What can you do immediately? What's the first thing? What do you have in front of you? Free food. What can you just grab? What formulas are available to you to just write down and substitute values that you have and just see where it goes? Can you do that? What are they talking about? Magnitude of the net average force acting on car A during the collision. Did we do anything with forces and momentum and impulse? Anything? Can you remember? Time, rate of change? No? Anything? Come on. You can do this. Think about it. We've done it a few times. We've done lots of questions. It's a little bit of a different situation with the graph, but it's definitely all there. All the information is in front of you. What can you do immediately? There's a formula that you can use. I know you know that. Go for it. See what you can get. Okay, hope you got it. I'm going to show you now. So the net average force, we know our formula for that. F net is equal to the rate of change of momentum. Okay, so impulse over change in time. Okay, so we have the changes in momentum, Pf minus Pi, and we have time. So to find a tangent is essentially to find a gradient. Okay, essentially finding a gradient, which is what we're going to do. So we're going to say Pf minus Pi divided by Tf minus Ti. It's a bit of a longer route. I know it's easier to just use the values and just go for it. You can do that. You can just say, okay, I can see with my eyes because I'm clever that 16,000 numbers divided by 0.1, right? That's fine. But this is just a more systematic way. It's either one. It's okay, whatever you like. Final time is 20.02 or 20.2. And sorry, I'm not doing time now, I'm doing momentum. Sorry. Okay, so momentum, final momentum is 30,000, initial momentum is 14,000, so 30,000, 1, 2, 3, minus 14, 1, 2, 3, and also they could be giving marks for this, so it's nice to just show all your working. I know we're smart people and you can do it in your heads because you're brilliant like that, I'm not actually. I had to use the calculator to find the 30 minus the 14, I know. Anyway, don't judge me. Just do it because you don't want to be losing marks because you didn't know, okay? And even worse, you don't want to lose marks for knowing but not rating. So just show how you got to it, okay? So initial time, I know it can be frustrating and tedious, but you need to to meet them halfway. Okay, they need to also understand that you know your work and you can just pull it out from thin air, because it's easy to fluke this. Okay, it really is. I know people that have, so 20.2 minus 20.1, and then you can say, okay, you can just put this whole thing into your calculator without having to break down any further. That's fine, as long as you show the initial substitution, then you're good. 30,000 minus 14, I'll do it with you, 1,000 divided by, okay, I'm just going to put 0.1 at the bottom because it's really, I get 160,000 newtons. And then we don't need a direction because it says magnitude only. And yeah, so I hope you realized through this equation that the force is the gradient of the momentum time graph, okay? And I also want you to realize that if that's true, then the other thing is, the converse is true as well, where the area under a time force graph gives you the momentum. Hope you can see that, okay? That's just things to take note of. So moving on, our last question, and we are done for today, and I'll see you guys next week. Remember, you can let me know at any point if you need anything, need any help. It's really, don't worry about it. So this is question 4, page break, please. New page. Now, I didn't actually want you to use 5 different pages today, but I'm just telling you to make a note that you need to do a new page. Because I don't want you to waste paper now, obviously. But actually, it's okay, waste it, because I know environment and all of that, but when you get 100% and you get a nice degree and then summa cum laude, magna cum laude, get a job, you can plant like 35 trees. It's okay. That's, yeah, it'll be worth it. Question 5. A pendulum. Okay, I haven't done pendulums with you guys, but it's just using energies, and I did teach you guys energies earlier today, so that's fine. Question 5. That's not today, sorry, last week, and I think you have managed to, I hope, watch the thing. So if you don't, it's okay. Energies, it's nothing crazy. I'll just show you a few simple things. So it's just a bob that's bobbing. Okay, cool, nice. Go for it, and it's banging into this thing, and it's pushing the block that side. Nothing crazy. Its height is decreasing, so it's very high here. It's not high at all. Ran out of weed, and so it's just doing a simple basic momentum pendulum motion. Okay, nothing crazy. Immediately after the collision, we get some values. Okay, so let's just draw a schematic, because I don't know what's happening from reading. Okay, I read books. Yeah, I'm a big novelist, but I can't extrapolate much from just reading all of this information and putting that words into my head and extrapolating formulas and maths. It doesn't work like that for me. I have to see the physical thing happening. So I draw. I do my schematic, so I know what's going on in the system. Okay, so there's my little sealing thing, and then I get, obviously ground is very, very important. Always draw your ground. Then this block that's here, which is 2 kilograms. Then I'm going to draw a bob. You can draw it out here because it's going to be easier. This is 5 kilograms, as the question says. You can open it up on your phone or whatever it is if you want to look at. And it is a certain distance off the ground, a certain height off the ground. So because we're dealing with energies, there are 2 important energies that we talk about. We talk about the EP, which is mgh, and we talk about the ek, which in here is 0. Okay, ek, which is half mv squared. You know that, right? Here the energy is just 0. There's nothing going on here. It's just chilling. It's chilling. So this is at A. Now this is going to swing down. Let's not do that. It's going to swing downward. Sorry about that. And then, oops. Get this nice. You can draw it separately also. That's okay. I just this is also fine. It stays the same, 5 kilograms, and here it has it at this point. There's an EP, which is mgh. But here H is a quarter H, okay? You can see that there. That's just what I'm showing. And then H over 4, 1 over 4 H, same thing. Don't get too caught up with the small things. And then the block then starts to move that way at 4.95 meters per second. And this is still 2 kilograms, all right? So here there's definitely going to be a nice EK that we can use. Yay! Here there's going to be EK and EP as well for us. Here at this point for this block before the collision. So you can see how I also illustrated before the collision and after the collision, but in different colors. Yeah, so that's the same kind of principle. Now for this part, let's check my notes. Make sure I'm not forgetting anything. Oh, you put your hand up. Yeah, Hamira, what's up? Sorry, I can't see your reactions because I'm not on the Teams. Did you want to say something? Is your
Yeah. Okay, so back to question for the last one. I'm a bit late, sorry. But we mixed up P final and P initial.
Oh, sorry, could you repeat that, please? My mic was off. My audio.
Sorry. So for question 4.2.3,
Okay.
the P final and the P initial is mixed up.
PF minus PI, P final minus P initial. Oh, yes, you're right. You are absolutely correct. Brilliant, brilliant spotting. Okay, cool. So the final momentum is going to be the 14,000. Sorry, it's just this thing that we have where the bigger number has to be first. That's not true. That can often lead to these kinds of mistakes, which you don't want to be making. Okay. Thank you for pointing that out. Why is this not working? Okay, erase this. Sorry about that. So 14,000 minus 30,000. Okay, yes, cool. So same value, what's going to be different is there's going to be a negative sign in here, right? That makes sense. Why does that make sense now? Because when the car collided with the second car, it lost energy. It lost, and you know, all these physical quantities are related to each other. So that loss in energy means the force of the other car was acting against it, and that decreased its energy and things like that. So it makes sense that it's going to be negative because the force is acting in the other direction. Cool. Hope that makes sense. Is that okay? Thank you so much for pointing that out. Yes, do make that change, please. And I just want to emphasize that. That's why, again, the systematic rewriting this out is a good idea. So do that when you have to use gradients and stuff. Do final minus initial. Okay. Hope that's fine. Thank you again. Right, let's go back to the stuff. Just want to look at something quickly. Okay, sorry, just looking at your constraints again in the CAPS document because I'm not sure how much detail and energy they expect you to know because I did it a while ago and we did a lot of stuff. But yeah, so I'm good now. Let's, oh, sorry, this is supposed to be an EK, right? EP and EK. Cool. Let's start answering questions, I guess. 5.1, blue. Calculate the kinetic energy of the block immediately after the collision. Immediately after the collision for the block, okay, EK is equal to half mv squared, half of its mass of 2, its velocity 4.95 squared. Let's get an answer. Okay, I'm getting 24.5. Sorry, 24.5 joules. Okay, so we need that measurement, that unit there. Joules, very important. You can use Newton meters also, I guess, if you like, but joules is okay. Now they want us to calculate the height h. How do we calculate the height h? Obviously, we're going to need to set up an equation, aren't we? So some sort of equation. So we're going to say total, this is going to be new for you to see, but basically there's a principle of conservation of mechanical energy, which you did do in grade 10, but I will refresh, of course, is basically energy is conserved. Okay, energy in an isolated system is conserved before and after. It's similar to the momentum thing. So it's nothing crazily new to you. So sum of the mechanical energy, EMEC or EM is fine, before is equal to sum of the mechanical energy EM after, Okay, this is going to be a little bit of a longish one because mechanical energy, EM, is equal to the sum of potential and kinetic energies. Okay, write that down somewhere. EM is equal to EP plus EK. They can ask you for that definition, just say it out in words. Mechanical energy is all the energies acting, okay? All right, so we're going to say EM of the block, oh, like that. So EM bob plus EM block is equal to EM bob plus EM block. Now we substitute some more. So the mechanical energy of the bulb at the top, yes, there is. The mechanical energy for the bulb at the bottom, yes, there is. But is the mechanical energy for the bulb, sorry, for the block before? No, there's nothing. Okay, there's really nothing before the collision. So we can just do that. Make sure you substitute, but we can cancel and say 0. Okay, you can do this here. On the other side, not so much because the block has mechanical energy, this has mechanical energy. So that's going to stay about the same. All right, so now let's keep substituting. So the mechanical energy of the bob means EK of the bob before, oh shoot, can do something quickly here because we need to sort of separate things. It can get a little bit confusing, but our notation again is very important. So I'm going to do a big bracket here and say before. So initial equals final. All right, that's good. As long as we're differentiating, it's okay. So here I'm going to now say EK of the bob initial. That's going to work better. Plus, oops, no. EK of the bob plus EP of the bob initial, there we go, plus 0 equals EK of the bob plus EP of the bob again, final. You can do it the other way around where you can put final inside here at the bottom. You can say EKF plus EPF and then write bob at the outside. I think that might have been smarter actually, but it's fine. But as I said, as long as the notation is correct, that's all that matters. EM of the block, so that's EK of block plus EP of block. Final. Okay, now we do the substitutions. Okay. So let me see if we can. Oh yeah. Okay. Anyway, let's keep going. It's a bit of a long one. So EK is half mv squared plus, I'm just going to do the things now because it's okay. We're just substituting. Plus mgh plus 0 is equal to half mv squared plus mgh. And I'm going to still put this bracket here. Say, yeah, that's fine. Maybe bob, because we established it's final already. And half mv squared plus mgh of the block. Okay, there we go. That should be fine. That's good. And let's substitute in here. Half mv squared. The bob, I don't know if you remember, was 5 kilograms. So half of 5 kilograms. But its velocity was 0, right? Oh, yeah. So we could just say that's 0 because it was stationary. Yeah, cool. But the potential energy was 5 times 9.8 times h. Okay, 5 times 9.8 times h That's fine. On the other side, half mv squared of the bob is just going to be 1/4 into 5 times 9.8 h. Why? Because again, the question said height decreased to 1/4 h after the collision. Okay, height 1/4 h. So you understand what's happening here, I hope. Okay, and plus mgh, mass of the bob, is the same 5. Oh, whoops. Okay, I swapped it around. Don't worry about that. Don't worry. There's no kinetic energy because the bob stops here. So EK is 0. So that's also 0. Okay, the bob stops and then the block keeps going. So this is just 0. Yeah, sorry. The only thing that's annoying with this is that it's long, but it's straightforward. You just have to make sure you do it slowly, systematically. You know where your values are coming from. You know where they're going, then you're fine. So here, half mv squared of the bob of the block. Sorry, the block is half, and then 2 v initial, and this is v final actually. Yeah, so which is 4.9 blah 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 squared. We don't have to substitute because we found it already. 24.5. 24.5 joules, and then mgh of the block is going to be 0 because it's on the ground. Okay, as long as you show the substitution, that's the important thing. Or you can have said that's fine, because you understand that it's not moving, then it's stationary. So yeah, okay, that's easy. That would save you a lot of time, I suppose. Sorry about that. Okay, now we know. This is set up fine. Now we're just solving for h on either side. All right, let's go for it. 5 times 9.8 h, 5 times, let's wait for it. Bring it all to one side first. So 5 times 9.8 h minus 1/4 times 9.8 h is equal to 24.5. Okay, now it's straightforward. So 5.98 h minus 1/4 of 5 times 9.8 h is going to be 3/4 of 9.8 times 5. Okay, h equals 24.5. Right? So I'm sure you know what to do here. Now you just take this here, and then you bring it over the side and divide 24.5 by it. So h is equal to 24.5, and you can use a big fraction, say 3/4 times 5 times 9.8. And let's get an answer for this. So energies is simple. You only need to understand one thing: conservation. Okay. Total mechanical energy equals total mechanical energy, and mechanical energy is equal to kinetic energy plus potential energy. So nothing crazy, as long as you just plot your schematic right and you know what's happening, you're following the motion, you know what's stopping, what's not stopping, where to get your values from, plug in your things right, and you're fine. Okay, 25.4 divided by 3/4 times 5 times 9.8. 2/3 or 0.67. That's my grade 10 student, 0.67. This should be closed. Okay, 0.67 height meters, whatever that is. All right. H is 0.67 meters. Yeah, that makes sense, I suppose. Okay, cool. And that's all your 7 marks there. That's the time. Okay, 15 minutes. Can we do 5.2 in 15 minutes? Yes, because I did it extensively in our last lesson. We were supposed to do more of these. Sorry that I didn't, but that's happening next week. So next week, the first half hour will be more work energy power practice, and it will be more organic chemistry in the second half, or the other way around. Go away. I don't really care right now. I don't do that to you guys, I promise. Okay, page break. Okay, not really. 5.2. Okay, so let's read. Block moves, blah, 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 normal things. I don't really, okay. Block does its, no, messages are not supposed to be coming up here. I'm not sure what's happening. I need to check my settings. Right, so blah, blah, blah. Don't need to know much here. You can see a slope, draw a slope. Okay, you know what we do. We start with our drawing. We've done plenty of them in the last lesson. I'm going to say 5.2 here. Don't say anything because these are separate questions. Okay, it's fine. Just draw. This is your question paper. I'm not even lying. You do these things on your actual question paper, right? This is what your answer sheet will look like when you give it into your teacher. Sorry, your answer sheet when you write your things to mark. This is what you're going. Obviously, without the red, but this is fine. Draw your things. Make sure that everything's there. This you can add in there. Yeah, everything. Don't worry about it. That's what I'm telling you. Your schematic needs to help you. Use it. It's a very good tool. So you know how we do these things. I'm starting and I'm not getting anywhere. Then we have a little thing there. We can go there. We have heights. Rob, I think you might have watched these today. If you didn't, that's okay too. You'll be able to catch up. So this is basically our method. We have a height there. We draw the object that's moving up. Usually we started with a trolley and we said 2 kilograms. And this is point B. This is point C. Okay, that's fine. Rough horizontal surface, etc. We know that this block is moving in that way at a velocity of 4.9 meters per second because it's on the diagram and it's in the question. -1. And we write EK here. We'll come back to that. Then we draw it to the top. 2 kilograms VF equals something. We don't know that yet. And, or do we know? Is it coming to a rest? Yeah, so we're going to say that it stops at points. Oh, no, it doesn't. The speed at point C is 2 meters per second. So 2 meters per second, -1. And here we have an EK. I'm going to do this in a different color. I'm sorry. And then we draw it in the middle, okay? 2 kilograms. That's our method. This is what we do. You know, we have a method for everything, whether it's kinematics, work energy power, electrostatics, electrodynamics. There's a method. Don't worry. Moving up here now, that's most of it, if I'm not mistaken. Right, so now let's put in our energies. So it's a 4-energy system. Frictional force, is there frictional force? Yes, there is, but that's what we're solving for here. Work energy theorem, that just means that the net work done on an object is equal to its change in kinetic energy. Okay, that's like 5 words. You'll be fine. Net work done on an object is equal to its change in kinetic energy. That's 2 marks. All right, now let's do 5.3. This is our method. So after we do that, we write our energies out. So we say EK initial equals. We say EK final equals. We say EP equals mgh. We know that. And then here we say WF, so the work done by friction. Okay, it's a 4-energy problem. So EK initial, we do this here, is equal to half MVI initial, V initial, whatever. Okay, substituting in there, half times 2 times 4.95. Let's get an answer. 4.95 squared. Oops. 24.5, that looks kind of cool. Oh, we knew this already. It's fine, 24.5 joules. Then we have EKF. This is 24.5, and then you put in a little block, okay? Your EK is going to block. EK is number 2. EKF is equal to half MVF squared is equal to half. Mass is 2 kilograms times 2 meters per second squared. Oops. And that's just going to be 4, I think, right? So yeah, half times 2 is 1 times 2 squared is 4. Cool. 4 joules. So this is equal to 4. To another block. EP, we know how to calculate EP, right? 3. EP is equal to mgh, which is equal to 2 times 9.8 times, is the height given? Yes, 0.5. So again, half basically. So it's just 1 times 9.8 is 9.8. So sometimes you don't need a calculator, but use one please all the time just in case. 9.8. And then did someone leave the meeting? Was that me? What happened there? Okay, everyone's here. Okay, cool. So here we just say, now we ring this, and WF is equal to frictional force times change in X. Okay, so we need to know how much inclined this block is in order to find the frictional force. Rough inclined plane, point C. Speed of the block up there is 2 meters per second. Point C is 0.5 meters above the ground. And during its motion, okay, no, they don't want the frictional force exactly, just the work done by it. Okay, no, then that's perfect. So WF, okay, cool. So from EKI, you do these arrows. Looks kind of crazy, but this is foolproof. Cool, and now we say, now that we have that done, we make a statement. What is our statement? Our statement, so 5.2, I'm going to pretend we answered 5.2 already, okay? I'm going to write down the equation, actually, so W net is equal to change in EK. This is exactly what we write down for 5.3 though, so yeah, never mind. So we write this down as the first thing, and then we split it up. We say EK initial, we leave some space, we put an equals to, we say EKF. We say, oh, the W gets a minus, the EP gets a minus because you're moving uphill, so EP is negative. If you're going downhill, EP is positive. So this is a plus. Kinetic energy is always positive, okay? And yeah, in this case, this sort of system that we use. So minus WF, that's the work done by friction, minus EP, that's the gravitational potential energy. Now we substitute EK initial is 20, skip a line, is 24.5. WF is what we're solving for. EP is 9.8. EKF is 4. And WF is what we're solving for, and that is our answer. WF is equal to, wasn't that easy? 24.5 minus 9.8 minus 4. I'm getting 10.7 joules. That's the work done by friction. And that's the entire paper. Okay, so that's 13 plus 13, 26, 11, 37, 45, 55. Oh yeah, now we do the multiple choice questions. So far we got 55 marks. Then at the end of your paper, you say, obviously after you left a page already, you say question 1, and then you answer your MCQs, okay? This you do afterwards. Please don't forget about it. So the tendency of an object is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6. I think that's all we're doing here that we can answer. Yeah, no, 1.5, okay, that's fine too. 1.1, let's do that. Let's see if we know that one. The tendency of an object to remain at rest, to continue its uniform motion in a straight line is known as inertia, okay, which is Newton's first law. The mass of an astronaut on Earth is m at a height equal to twice the radius of the Earth. The mass of the astronaut will be what? So we know our equation. Oh wait, no. Mass doesn't change. Okay, mass is constant. So the answer is C. See how they're trying to trick you there? M. So the mass of the astronaut on Earth is m. The mass of the astronaut on Jupiter will be m. The mass of the astronaut on the Sun will be m. The mass of the astronaut in the core of the Earth will be m. Wherever he goes, his mass stays the same. The weight changes. That's important. So they try to trick you. An object is thrown vertically upwards from the ground. You know this one. We've done it. Which one of the following is correct regarding the direction of the acceleration? Okay, acceleration is always downwards. Always happens downwards. Yeah, so the answer is going to be C. Acceleration does not go upwards when you're moving down. It does not go downwards when you're moving up. It always pulls you down. All right. So they want to know, yeah, the direction of acceleration does not change under any circumstances. 1.4, a person drops a glass bottle onto, sorry, I don't know why I saw blue, onto a concrete floor with a certain height, and the bottle breaks. The person then drops a second identical glass bottle from the same height into a thick woolen carpet, but the bottle does not break. Now think, before we look at the rest, think about this. What did I tell you about the car's crumpling system, right? In momentum, impulse. When a car that can crumple quicker, okay, it's like softer bumpers and things like that, it increases the collision time. When you increase the collision time, because time is inversely proportional to force in that equation, you decrease the force of the collision, so people are safer. if you get a harder ball, that's why, like, harder balls don't bounce as much as softer balls, because less collision time. So a harder bump on the calf, you have like a metal girdle or something, it decreases the collision time and increases the force of the collision, right? Anyway, let's look at the question. Which one of the following is correct for the second bottle compared to the first bottle for the momentum change, the same momentum change? So the second bottle fell onto a thick woolen carpet. The first bottle fell onto a floor. That's why when you throw the bottle onto a thick woolen carpet. God, these are the grade 10 people. They're very like clingy, hey? Let me just send them a message to let them know that I'm starting soon. It's 5 minutes early. What even? Jesus Christ. Calm down. No, it's not the same as last time. Okay, cool. Very enthusiastic, these guys. Anyway, they didn't do enough to get dead behind the eyes yet, like you. So the average force in the second bottle is going to be smaller. Okay, so B or D. The time of contact with the carpet is going to be larger, so C or D. The only overlap is D. So smaller average force, larger time of contact, D. I hope you understood why that's happening, right? So you see how they can test these concepts? Very cool. A block of mass M, there's still time, I don't know why they're fussing, is released from rest at the top of a frictionless inclined plane as shown. The total EM is EQ at the top of Q and ER at the point R. Kinetic energy of the block at Q and R is KQ and K. Okay, respectively, this is notation. The question is, which statement is true regarding total EM and the kinetic energy of the blocks at points Q and R? So Q is at the top, R is at the bottom. What's the difference? Height, okay? The block at Q is much higher up, so that's going to be having an EM. The block at the bottom is going to be have no EP. There's no EP at the bottom. So the EK at the bottom is going to be large because the EK consumes the EP. Do you understand that from this equation here? EM is equal to EK plus EP. So if there's no EP, EK is the whole EM. EM cannot change. EM is the same all the time. So that amount stays the same. If EP drops, EK has to pick up so that this EM stays the same. If EK drops, then EP has to increase in order for EM to stay the same, okay? Because that doesn't ever change. Think about it like this. You have 1 equals x plus y, okay? So if x is 0.6, y has to be 0.4. If there's no y is 0, x has to be 1. If x is 0.25, y has to be 0.75. So they sort of like, I hope you understand what's happening. Yeah, one drops, the other has to pick up to keep the sum of them the same. So at the bottom, there's going to be more EK at the top because at the top, there is EP. EP does exist. So they're going to share the EM. At the bottom, there's no EP. So EK is greedy. It just takes all the EM for itself, right? So what's happening? This is the last one. Total mechanical energy, Q. Okay, total mechanical energy doesn't ever change. So it's going to be B or C, right? The total mechanical energy does not ever change in an isolated system, which this is. And if they didn't say, just take it as it is because that's your syllabus. So either B or C is correct because they want to compare points Q and R, and the total mechanical energy at Q and R are the same. So it's either B or C as an option. But the kinetic energy, let's look at that. So we know that KR is going to be greater than KQ, which is shown by B, okay, where KQ is smaller than KR. So our answer has to be B there, right? So this is 10 marks. So 10 plus 55, 65 marks. So that's 65 out of 150 marks of your final exam paper that you can answer successfully, right? Isn't that kind of cool? 65 is a lot. 65 out of 150 is, I don't know, I'm not that good at maths. 65 divided by 150. It's about 43%, okay, which is a passing mark, right? Significant amount. So, and we're already in, well, we're not even in March yet. So you still have so many months more to go, and you can get 43% of your syllabus, of your marks, like that. So this is just to point out that we are making progress and that you don't have to worry. Just keep working consistently, dedicatedly, committedly. Know what you want out of this, and keep focusing on that and keep going at it. Physics every day, guys. I would suggest taking the 2017 paper. I can send it to you if you want, and doing the same thing that we did here today. See what you can answer. If you struggle, show me. Let me know. Refer to your notes. If that doesn't help, ask me, and try and